Okay. Well, thank you. Thank you for having me here. This is quite a different audience than I'm accustomed to. I'm going to play things a little bit by ear, I believe. And I want you to ask questions as we go along. The objective is understanding global warming. So don't hesitate to ask. And I'm going to have questions for you too, just to make sure you're on your toes. Here comes the first question. Is your cell phone turned off?
Can I ask a quick question?
Okay.
Your background sounds like it's mostly solar observatory work. How does that translate into Earth climate science?
Well, the question is, I'm a solar astronomer, so how is that relevant to this topic? Turns out understanding the sun has a lot to do with global warming. In particular, we need to know whether the sun has been changing its output, and it is not, except for the 11-year cycle. It seems to have been very nicely constant for us, or very nearly so. But actually, my academic background is in astronomy in general, and glad you asked that because leads to the next slide. Here's a good astronomy problem for you. What is it that determines the temperature of a planet? And this is something that astronomers deal with all the time. In the case of the Earth, the temperature has been changing, and we call that global warming, which is one of the outstanding issues of our time. Now, there's a science aspect to this, and there's also a political one. And the political one goes to questions like, should we do something about global warming, and what would that be? And that's where all the contention comes from. But this is a science cafe, and we're here to talk about the science that goes into the study of global warming. Now, I want you to keep a few points in mind. I'm going to be showing you data, a lot of data. And in fact, we're going to see how far we can get with this subject on data alone. And then we'll put in some physical understanding as well toward the end. But I want you to remember that we talk about global warming, we're talking about changes in temperature. And I'll remind you that from time to time. We're also going to use the Celsius temperature scale. And 1 degree Celsius is bigger than a degree Fahrenheit. It's almost twice as big. So if you hear about a change of a couple of degrees Celsius, that's perhaps more like 4 degrees Fahrenheit. And there was a question here.
I was going to say, because there's a big controversy about global warming, whether it's true or not, but like my grandma has an issue with it, and I tell her because she says it's getting cooler. Is it because the warm air is pushing the cool air further down? Or?
No. The question was whether global warming comes from pushing the cool air pushing the warm air down.
No, because certain areas are getting colder while others are getting warmer.
Oh, yeah.
Pushing it,
Yeah.
like, in that general direction.
Yes, global warming is not uniform over the Earth. There are some areas that are warming up very fast, and others not. And that's to be expected. Okay. Now, I want to reorient you a little bit as I go along here. Everybody thinks about global warming. Oh, that's the air. What we need to learn right away is that it's absolutely essential to consider the entire climate system. And I'll get to that point as we go along here. All right, let's look at some data. Now, this is a plot of temperature on the vertical scale, actually temperature change. I've underlined that. And the year is on the bottom. And this graph is titled Change in Global Mean surface temperature. It's from 1850 to 2012. This is constructed of millions of measurements that are taken at thousands of locations all over the world. And if we look at this, you'll see that we're plotting now change in temperature. We're not plotting temperature. What's done here is that all of these various points on the Earth are having their temperatures taken, and changes over the years are noted. And then it's the changes that are reported to a central data bank, and those changes are all averaged together. So as long as we're working about change, it does not matter where you put the 0 point on the scale. It's relative. It's all relative. And so you see here that our 0 point is like late 20th century. And if we look at our old records from the past, and you see there's a lot of jiggling around, it's not a steady march of temperature change. And here we are up today, and over this span of time, you see here, temperature's going up about 0.8 of a degree Celsius, which is a big change, actually. I'm going to come back to this graph in a minute, but let me now ask you the second question. How many of you have seen this graph or something like it? Okay, that's pretty good. I'm glad to hear that. You know, if you listen to the news, or even watch the news on television, they talk about temperature change, and you'll see one guy saying, well, it's going up, and another guy says, no, it's not. But how often do they put this plot up on the screen for you to see for yourself what's going on? Almost never. So I'll ask you another question. You look at that graph, is temperature going up or not?
Yes.
Yeah. You would say in the long run it's going up. Well, temperature measurements have been of interest to people for years and years. And some of our founding fathers were pretty into this in a big way. Thomas Jefferson, even while he was president, was making temperature measurements in his backyard. And James Madison did too. Now, in a way, perhaps we don't think this is too surprising that our founding fathers would do something like this. They had such broad intellectual interests. Perhaps this is no surprise. Presidents probably had more time on their hands back in those days. I mean, can you imagine now the President of the United States out in the Rose Garden of the White House making temperature measurements? No. What do we mean by global mean temperature, global mean surface temperature? Well, it's 30% air temperature over land, about this high above the ground, 5 feet or so. 30% air temperature measurements above land, and 70% either sea surface, water temperature on the surface, or air temperature over the water. Doesn't matter which one. Why would we choose these percentages? 30% land, 70% over the ocean. Why?
They reflect the proportion.
Yeah, right. Yeah, the Earth happens to be about 30% land and 70% ocean. All right, so that's no big surprise. Now we go back to the first slide. I'll just say a couple more words about this. The gray band that you see on here shows the range of uncertainty in the measurements, and they're statistically constructed. And these are what we call the 95% confidence interval, which just says that the real answer to what the temperature is 95% probability within that gray band. And so the solid lines that you see here are sort of going right down the middle. The colors, the black, the red, and the blue, represent 3 different research centers that analyze this temperature data. There's 1 in Britain and 2 in the United States. And again, I remind you, 0.8 of a degree rise in temperature since 1850, roughly. Okay, let's look at just land, just the land temperature. Temperature rise 1.3 degrees Celsius. bigger. And here's sea surface temperature, 0.6 degrees Celsius over the same time period. Interesting. Now, a little math problem for you to try sometime. If I tell you the temperature rise over land is 1.3 degrees Celsius, and over water it's 0.8, or 0.6, I'm sorry, then can you show that a global mean surface temperature rise of 0.8 degrees Celsius is a reasonable result? You might want to try your hand at averaging those numbers out according to the percentage of temperatures that are over land and over water. Now, here's the thought question for you. Why is air temperature over land rising faster than sea surface temperature? Anybody have an idea? Okay?
Because when air, it can move, but it still has the sun shining, like the solar rays. So
Oh.
it heats it up more.
Okay, it heats it up more, yes.
Like the water has more of the current and the tide pulling it back and forth.
Okay, it does have to do with differences between air and water, that's for sure. Anybody have anything else to add to that? Vegetation,
Lack thereof.
or lack thereof. Well, I'll ask you another question. Is it harder to raise the temperature of air or harder to raise the temperature of water? Water is really, has a lot of what we would call thermal inertia. It's difficult to raise the temperature of water. So as the air gets warmer, the water temperature lags behind in temperature rise. I'll get you thinking like a climate scientist here before we're done. All right, with what we know now, I'll ask you yet another question. Which of Earth's hemispheres, north or south, would you expect to be warming faster? The northern hemisphere, indeed. More land as compared to the southern hemisphere. All right, I think it's time to look at the whole climate system. There it is, atmosphere, ocean, land surface, and lots of ice and snow in certain places. We talk about the climate system as containing these four major components because these four things interact with each other. They can exchange heat between one another. So you can't look at just one of them and think you've got it made. You've got to consider how the whole system is coupled together. And now I remind you again, we'll look at global mean surface temperature. That's shown by the red dashed line. And now we see something here that's a bit troubling. This global mean surface temperature that everyone talks about represents just a tiny part of the whole climate system. It's just that little skim along the surface there. And it doesn't include what's down deep in the ocean or high in the atmosphere. So maybe we have a problem here. So if we want to find out what's going on in the climate system, we need to assess all parts of it. We need to measure changes everywhere. And actually that's been done. You just don't see it on the news. So let's just see what's happening, just in rough terms. If we look in the atmosphere, we see here the atmosphere is broken down into the troposphere, which is where most of the weather happens, and the stratosphere, up where the jets fly. And if we look down at the bottom of the troposphere, the temperature's rising fast, and it rises fast up through the middle troposphere. And then as you get up toward the top, the temperature rising more slowly. You get to the stratosphere, temperature is falling. And of course, ice and snow is melting, and the ocean surface temperature is rising fast. But down deep in the ocean, it's hardly changing at all. And the land surface temperature is rising as well. Yeah, question?
How do you know the temperature's falling in the stratosphere? Do you have a satellite up there or something? How do you tell?
Yeah, there are satellite measurements. That's the best way to do it right now. There are some measurements that go up into the very bottom of the stratosphere that have been done by in situ probes, balloons or whatever, radiosondes. But the preferred way now is to use down-looking satellite measurements.
A question.
Yeah.
This might be a good chart. Recently, there was a discussion about the Atlantic Ocean absorbing a lot of the heat, and
Yep.
at some point that will end.
Yep.
Can you explain that a little bit using maybe some of this?
Yeah, the question goes to how the ocean may be modifying surface temperature. And as I mentioned before, there is interaction between the atmosphere and the ocean. Heat can be exchanged between them. And it depends a lot on ocean currents and whether they change. And I will get back to that a little later. Are you puzzled by this temperature falling up here? You know, that's an interesting thing. I'll just give you a little clue ahead of time. If global warming was happening because the sun was getting brighter, then the stratosphere would be getting warmer too. So this is one way you can rule that out. Of course, the other way is you just measure the brightness of the sun. But actually, this fact that the temperature is falling up there is a part of an important clue as to what's going on. Now, another thing about this is that some temperature changes are worth more than others. And as we already discussed, it requires more energy to raise the temperature of water than to raise the temperature of air. I'll give you a few specifics here. A lot of laboratory measurements have been made to determine how much energy is required to raise the temperature of various substances by, say, 1 degree Celsius. And we're going to use an energy unit here of joules, but you don't need to know what it is. This is all relative. I could have used calories or kilowatt hours. Doesn't matter. It takes 1 joule of energy to raise 1 gram of water by 1 degree Celsius. And rock, actually a little bit less. Kind of surprising. You can put a gram of rock in your hand easily enough, but a gram of air is big, right? It's less dense substance. Water takes more than 4 joules to raise the temperature 1 degree, and to melt a gram of ice, 334. Tremendous amount of energy required, relatively speaking, to melt ice. So when you see the world's ice melting, that tells you that that's a tremendous amount of energy has been put into the climate system. I'm going to skip that section there just a minute. But I brought up this subject of energy for a very important reason. As soon as you express everything in terms of energy, then you can add all these parts of the climate system together. You can't do it if you use temperature because all these temperature changes are different in different parts of the climate system. But if we have laboratory experiments that show us how much energy is required to melt ice or raise temperatures of substances, then we can take the mass of the atmosphere and the mass of the ocean and the mass of the ice that's melted and the mass of the rock and soil under our feet where the temperature is rising. And you can find out how much energy has been required to raise those temperatures. And when you do that, you come up with some absolutely startling result. These numbers are very big. They're expressed in billions of trillions of joules. The atmosphere's temperature has gone up that 0.8 degrees Celsius. That's required about 3 billion trillion joules. It has actually taken more energy to melt the amount of ice that's melted so far, or to raise the temperature of the land surface. And a whopping 255 has gone into raising ocean temperature. The bottom line on this is that most of the energy from global warming has gone into raising the temperature of the ocean, over 90% of it. The ocean is sort of the master of the climate system in terms of its ability to soak up energy. And the ocean is also important because it transports heat due to the ocean currents, which can flow north and south, east and west, and up and down. Okay, I did this little diversion for a very good reason. And you may have heard statements just in the last few years. Global warming is over. Temperatures have stopped rising. How many of you have heard that? A few of you have, okay. I get pummeled with this all the time, actually, but I'm going to use the result that the ocean is really the big absorber of heat to show you what's really going on here. The question is global warming over? What the question refers to is this right here. If you look in the last 10 years, there has been very little change in surface temperature. Right there. Very little change in surface temperature. Actually, look at this. Was global warming over down here? Apparently not. There was a 30-year period when temperatures actually came down a little bit. So there are things going on here that have to all be considered in order to match how this temperature curve is rising. Okay, so the claim is, and they're politically inspired, I've got to tell you that. The surface temperature has leveled off, therefore global warming is over. But remember where the real action is in the ocean. That's where most of the heat from global warming has gone. And look at this, here's the change in temperature in the upper half of the ocean. That's the upper 6,500 feet of the ocean. And look at that. There's been no leveling off. There has been no leveling off. So if you look at where most of the heat is going, you could never make the claim that global warming is over. And we can talk a little later about why this is still rising and this one is sort of leveled off, at least temporarily. Any other questions? Yeah.
I think I have two.
Two questions, all right.
All right, I'm thinking of the ocean in terms of the battery for heat.
Okay, he's thinking of the ocean in terms, analogies to a battery, okay?
And then with the subsurface temperature and the ice, I'm curious as the surface temperature and the subsurface temperature. Is the fact that we're losing icebergs, is that keeping the drink cold underneath since the water, the ice, I'm having a hard time wrapping my head around this, but the ice that's melting.
The ice is melting, but that's not the reason.
Okay.
That's not the reason why.
I was curious.
The ice has been melting all along.
Okay, but not any increased rate that reflects.
No, that's right, yeah.
Okay. Thanks.
I noticed the time period is also along with advances in technology, if you think about it. Because here we're at the lowest, where it's regular, it's during the time when we didn't have a lot of things like computers. And as we get more advanced, it gets also higher. Is it somehow related to technology or no?
Well, the way technology would affect this data is in the quality of the measurements. I think that's the way it would enter in. And in fact, technology is better now, and you'll notice the width of the gray band. The uncertainty in the global mean temperature measurements now are only a few hundredths of a degree C, whereas back in this time they were several tenths of a degree C. And that's because we have better ways of measuring temperature, in particular under the surface of the ocean, and there are more surface stations, and there's more consistent reporting.
So can we actually be really sure that it's like that? Could it have been more or less back then?
Yes, and remember, these are the 95% confidence limits. It's not impossible that the temperature was outside the gray band. The probability of that is low, okay? So what we're saying is the gray band tells us that there's a 95% probability that the actual temperature is inside the gray band, okay?
Alrighty.
Yeah. And it's derived from a statistical analysis of all of the individual stations that have been used to collect the data. And to get ocean temperatures down deep in the ocean, they use remote devices that dive down. They go up and down, up and down. And they too are now making thousands and thousands of measurements.
Excuse me, I actually want to reiterate her question because as it's gone up, there's also been more industry, more generation of greenhouse gases.
Absolutely.
So
Yeah.
there is a relationship between what she was calling
Right.
technology.
That goes to the cause, yeah. Yeah, technology is certainly related to the cause. Yeah. Question?
Yeah, I'm just curious, they recently launched a, I think it was called a CO02
Yeah.
satellite.
Yeah.
Now, does that impact the measurement of water temperature, or is it just earth temperatures?
That satellite, its primary mission is to measure the concentration of carbon dioxide.
It's not measuring temperature, it's measuring.
There may be a down-looking temperature sensing device on the satellite. I'm not sure. There are a number of those. That's getting to be a more common thing nowadays.
Does it, can it measure, is there carbon dioxide in the ocean as well?
Oh, yes.
So it can measure that as well?
No. No, it will. No, that satellite does not measure carbon dioxide in the ocean. Okay, carbon dioxide in the ocean is measured by other techniques. I think what you'll find is that the satellite measurements are interested in pinpointing areas in the Earth's atmosphere that have more or less concentrations of carbon dioxide. Find out how the sources of emission of carbon dioxide are varying over the Earth. That's a principal result everybody wants to know. Did I answer your question sufficiently? Yeah. Yeah.
Well, considering what you said about the thermal inertia of the oceans and looking at the significant rise right there, is there going to be a tipping point where there's nothing we can do to stop the rise of temperature in the ocean?
Yeah, the question is about tipping points. A tipping point is what we call, it's a temperature threshold, which when exceeded, disallows temperature to fall back to its original value, even if you cut off the sources of whatever's raising the temperature. There are possibilities there in mind that almost impossible to predict precisely. One tipping point that you hear about has to do with permafrost and subsurface ice, frozen land and soil at the high latitudes on the Earth. And as temperature rises, the permafrost will thaw. And as it thaws, the vegetation that's in there will decay into carbon dioxide and methane gas, both of which are greenhouse gases. So the question is it possible for the temperature to rise to a point where the emission of carbon dioxide and methane from thawing permafrost is greater than the part that's produced by man? If the answer to that question is yes, then you have crossed the tipping point. So that would be an example of one of them. And a lot is made about that because it's really newsy, you know. But at this moment in time, I would say that tipping points are not predictable in any precise way.
Tiny question. Are you going to address why the subsurface temperatures are rising?
Yeah, I certainly will, yeah.
Okay, cool.
What's causing global warming? And I should start talking about this a little bit. One idea is that well, maybe there's an increase in solar radiation. This is something that has been done to death. There have been a number of satellites that have very precise radiometers in space, and they've been monitoring the solar output since now about 1979. And there is no upward trend. There is an 11-year cycle of solar activity. It goes up and down slightly with an 11-year period. But the long-term average is not going up. In fact, it's slightly downward, probably, over the last 10 or 20 years. Solar radiation does not appear to be the answer. How about energy coming up from below? Heat from the Earth's interior. This is another one that's been discussed. And again, the answer is almost certainly no. The amount of heat that's coming from the Earth's interior is very small, and there's been no observed change in it. Indeed, the Earth is very hot on the inside, but all those thousands of miles of rock between us and the middle of the Earth are very good insulators. And then there's this thing called the greenhouse effect, which I will get into as we go on here. And the greenhouse effect has to do with greenhouse gases, which are gases that absorb the Earth's radiation that's trying to escape back out into space. The Earth is always trying to cool. As the sun warms it up, the Earth tries to cool itself by radiating its energy back into space. And greenhouse gases block that radiation. And that's the essence of the greenhouse effect. And I'll talk more about it because it's such an important concept. What about other things? Use your imagination. The changes are so big, the changes are so fast that something else in nature, you would almost surely be seen immediately. But who knows? When I talk about other things, would you allow me to rule out death rays from Mars? I had a student once, and he was absolutely sure that it was radiation from Jupiter that was causing global warming. Now, fortunately, ideas like this can be checked in science. All you have to do is point a telescope to Jupiter and measure the radiation that's coming off of it. And of course, the answer is, nah, nowhere near. All right, let's talk about some of these greenhouse gases. And let's talk about temperature a little bit further back in the past. Remember that the data I showed you went back to 1850. That's right about in here somewhere. And that's the modern temperature record, this solid black line right here. It's been smoothed out, so it doesn't have all the jiggles in it. And it comes down here like this. That's the instrument record. Thermometers, if you will. Now, what if you want to go further back in time? Well, you have to use something that substitutes for temperature, and these things are called temperature proxies. These are things in nature that are sensitive to temperature and which can be measured on the basis of historical changes in the past. For example, tree rings, coral formations, ocean sediments, and so on like that. Isotope ratios in ice that's been in ice core measurements that have been made in the polar regions. And as the layers of ice build up in time, you can drill into them, look back into time, and measure ratios of atomic isotopes that are sensitive to surface temperature. And there are quite a number of these things. And as you can see them here, there have been so many attempts to reconstruct Earth's temperature back 1,000 years or more. And there they are. And you see these measurements aren't as precise. Obviously, they're all getting somewhat different temperatures. But one thing that you can see from all of this is that relative to today, these temperatures were lower back then than they are today. All right, I wanted you to see the data. It's important to see what we're actually talking about here. Yes, there is uncertainty in these measurements that go back in time. And that's one of the things we have to account for. Question here?
I'm just wondering if some of those proxies are more reliable than others.
That's probably right, and I wouldn't want to get into that. I'm probably not a good person to say. Yeah. And it's a question about where they are on the Earth as well. For example, the measurements of ice are always in the polar region, and temperature there is changing faster than other places. And there's another question here.
Yeah, are you going to discuss the different types of greenhouse gases?
Yep. Yes, I will discuss the different types of greenhouse gases.
Okay, one of the things I noticed is that, like in most of the areas, all the lines seem to be kind of spread out.
Yep.
But at the very end, there's that one part where they all spike up at the same time.
Yeah.
Right about the same temperature. I
Yeah.
noticed like that's the spot where they all seem to be the closest.
Yeah, yeah. Every temperature reconstruction is given one line on this graph, and the errors in each of them are not included. But this one that you see here that's going up is the temperature measurements that are made with thermometers or instrument measurements. And so there's only one of them there for that reason. But really, if you get down a little further, right down here at about into the 1950s, you can see that there are some of these proxy measurements here, and you see they seem to be more accurate or more consistent with one another here than they were in the past. This data is difficult to acquire. Now that's the temperature back 1,000 years or more. I'm showing you that on the top. And now down below are the changes in greenhouse gases. Not all of them, but the three main ones: carbon dioxide, methane, and nitrous oxide. Don't worry about the concentrations on the vertical scale. We're just looking at this in a relative sense. And what you see here, we have this rapid rise in the concentration of greenhouse gases beginning down here about the same time the temperatures on the surface are rising. Now, since the 1950s, this concentration of these greenhouse gases have been measured by direct sampling of the atmosphere. If you go further back in time, you can pull a really good trick here. You drill into the ice and you look at the air that's trapped in bubbles in the ice, and you can measure the age of those by the layer of the ice that they're in, and thereby you can measure the concentration of greenhouse gases way back in time. And that's where these data are coming from, prior to about 1950. So there are the greenhouse gases. I'll say more about them in just a little while. And again, I'm going to skip over a couple of things here. And I don't know how detailed I can be about the greenhouse effect, but I want to give it to you in a nutshell. And then if we want to pursue it in more detail, we can come back to it. We're not talking about data anymore. Now we're bringing in physical principles that are allowing us to determine from the data that you've seen what's going on. Here's a cross-section of the Earth. The sun is the big energy input to the climate system. It's visible light. The atmosphere is more or less almost entirely transparent to it. The visible light comes in, it warms the surface of the Earth. The warm surface of the Earth radiates at infrared wavelengths, not visible light. Everybody's heard of infrared cameras, these night vision things and so forth. This is the thermal infrared. The Earth is radiating its energy back in space. What's going on is it's trying to establish an equilibrium between the amount of energy coming in and the amount going out. Those two quantities have to be kept equal, or at equilibrium, what we call equilibrium, they are equal. And under that condition, the surface temperature of the Earth remains constant. Now, if I increase greenhouse gases here in the atmosphere, I reduce some of the energy that's coming out. And in fact, some of it is then re-radiated back to the surface of the Earth. That raises the temperature of the surface of the Earth. And as the temperature rises, then the infrared radiation slowly increases until it again equalizes with the amount coming in. So it's really pretty much a no-brainer. If you add greenhouse gases to the atmosphere, global temperature is forced to rise. And there's nothing new about it. The greenhouse effect has been understood for more than a century. There's a well-known mathematician that some of you will get to know if you go to college, Joseph Fourier. Back in the 1820s, he suspected that this was going on. And he actually described the concept of the greenhouse effect as I've just explained it to you. A little later, John Tyndall in England measured the absorptive properties of some of the greenhouse gases that we know now, carbon dioxide and water vapor. And then toward the end of the 1800s, Svante Arrhenius, who was a Nobel Prize winner in chemistry, he actually made the first climate models where he calculated how much Earth's temperature would rise due to an increase in carbon dioxide, or how much it would fall if carbon dioxide were to decrease. He had no idea that industry would ever make enough carbon dioxide to increase the Earth's temperature. He was more interested in what caused the ice ages, and did a reduction in carbon dioxide lead to a cooling of the Earth? And in fact, it does. Let's look at some of the greenhouse gases. Water vapor is the most important one. The water vapor isn't made by man. It's entirely natural. Carbon dioxide has natural sources and man-made sources, or what we call anthropogenic sources. Methane is another one, both natural and man-made. Nitrous oxide, natural and man-made. And then there's a whole other group of materials that we call halons, they're refrigerants, sterilizers, and a number of others. They're 100% man-made. And there are dozens of other greenhouse gases. Some are natural, some are man-made. The most important ones are listed here. Yeah, question?
I noticed the only one that doesn't have man-made stuff in it is the water vapor. So a lot of the stuff we use ends up in the atmosphere.
The water vapor?
No, besides what?
Oh, yeah. Yeah, absolutely. Yeah, anything you do that uses energy, if it's not solar energy.
So we
Yep.
as people
Oh,
play a large
yep.
part in greenhouse gases.
Yep. The carbon dioxide is the most important man-made greenhouse gas. And the primary source of it is electric power plants generating electricity. Transportation generates some as well. Land use changes, forestry is involved as well. Waste disposal produces methane. Natural gas industry produces methane. Agriculture produces both methane and nitrous oxide. Well, it's interesting to think about whether there's other evidence for the greenhouse effect other than what I've just told you about understanding the physics of what's behind it. Now, you probably have had enough science in your backgrounds, and everybody knows that what you like to do in science is to conduct a controlled experiment. So here's a controlled experiment for you. I take one Earth, and I don't change the atmospheric composition at all. That'll be my control Earth. And then I take another Earth, the one that we have now, where the greenhouse gases are rising. And then we just see what happens, what's going to be the difference in the temperature. Well, of course, we cannot do this experiment. We've only got one Earth to go with. But there are two things we can do. We can look at Earth's temperature in the distant past when greenhouse gas concentrations were different than they are now. That's one thing we can do. Or we can look at other planets that have different concentrations of greenhouse gas than Earth does, and see what's going on there. So let's try the first one of these. Let's look at Earth's temperature in the past. On the top is temperature change actually, and we're looking at the temperature in the deep ocean now. So we're looking at where most of the energy from global warming is going. And if we start here at the present day, which is 0, and these data are good enough to go back even like to 60 million years ago, and we see that ocean temperature was a lot higher back in those days. Where do we get these temperature measurements? Well, again, there are geochemical markers from ocean sediments primarily. Living organisms store chemicals in their bodies according to what their temperature is, and there are a number of them, things that have been used, and they're all giving us a trace that looks something like this. And then we compare that temperature change in the past with atmospheric carbon dioxide. And it's quite a bit different in the past. Today, we have a concentration of about 400 parts per million of carbon dioxide, but it was easily 3 times that here about 50 million years ago. And these measurements too come from geochemical analysis of a number of things, soils, ocean sediments, and so on. So the pattern exists in the past as well as in the present. Another thing we can do is compare a couple of planets, and I'll just do 2 of them here. All of the planets have been looked at for how to understand what the temperatures are through the atmosphere. But Venus has a solid surface, as does Earth. And we can calculate what the temperature of Venus ought to be based on the amount of sun radiation that it's picking up, and Venus and Earth. And Earth really should be 18 degrees below 0 Celsius, just based on the amount of solar energy that it absorbs. But actually it's 15 degrees C, 15 above 0, and the difference is 33 C. So the greenhouse effect is doing us a favor, isn't it? Otherwise we'd be all frozen to death. If we look at Venus and do the same thing there, it ought to be 33 degrees below 0 Celsius, even colder than Earth, even though it's closer to the sun. It has very reflective cloud cover, which prevents much solar radiation from being absorbed. The surface temperature, however, on Venus is almost 500 degrees C, which is hot enough to melt some metals. And you look at the difference between the expected and the actual, you see that Earth is here at 33 degrees C and Venus is 510 C difference. And then we look over here at the amount of carbon dioxide in the atmosphere, and it's 0.04% for Earth and 96% for Venus. So again, we see the rule before our eyes that greenhouse gases raise the surface temperature. Well, I've come to a place where I should stop showing you slides about the science part of this. And I don't know where you want to go with this. We can talk about the science, or we can talk about some of the impacts of global warming. Anybody have any suggestion as to where we want to go with this? Yeah.
I want to know some of the impacts because I mean we can know all about it, but how would it fix it if we don't know where we're doing it wrong?
Okay, there's a vote for throwing up something about impacts.
I misread and thought you had solved this.
No, I don't solve the problem. Thank you. All right, well, let's go ahead and look at some impacts. On the left here is a table of some of the physical changes that come with global warming. Now, number 1, there's temperature rise. Number 2, there's sea level rise. And that comes from a warming ocean and also because we're melting ice. the water vapor content of the atmosphere goes up because a warmer atmosphere holds more water vapor. These are physical phenomena. I'm not talking, in this table, I'm not talking about what it does to mankind. These are things that you expect directly just from the scientific context of everything I've told you. We expect changes in ocean circulation, and some of that seems possibly happening now. Changes in weather patterns, that's expected. We might be seeing that already. Acidification of seawater, that happens because carbon dioxide is dissolving in water and changes the ocean chemistry. Ocean salinity distribution changes, loss of permafrost, which is what we mentioned already. The anticipated impacts to society, and I'm no expert in this, but in most respects these are no-brainers, and they've been discussed a lot in the press and everywhere else. You know, changes in the zones where we have arable land because of changes in rainfall patterns and temperatures. Property loss from floods or from rising sea level. All kinds of reasons for economic loss. Insurance rates will probably go up. Things like flood insurance, or they have insurance, I believe, for agricultural purposes as well. Adaptation costs. As sea level rises, we're going to build dikes to protect Miami and New York and so forth. That would cost a lot of money. Populations may have to move. There'll be probably health impacts. Natural species are going to move in response, or they may have their populations cut back if they don't.
What is extirpation?
Extirpation means almost extinction. You haven't quite wiped it out, but you've reduced the population to exceedingly low level. And by the way, some of these horrific climate changes that have been seen in the past have been associated with extirpations, and actually extinctions as well. Dead zones in the ocean where there's a low oxygen supply. Other things happen that many people will consider beneficial, like the Arctic Ocean will be open for shipping.
Would you mind just talking about dead zones?
Dead zones?
Yeah.
Yeah, sure.
Why are there specific dead zones?
Visualize this. The ocean is full of living organisms. Plankton in particular, a tremendous amount of it lives in the upper levels of the ocean and some in the deeper levels as well. When that plankton dies, it sinks. And as it sinks, the oxygen in water starts to decompose the organic materials and it produces carbon dioxide. So the oxygen in the water level decreases as you go down. Now imagine that we have global warming that reduces the circulation in the ocean, that resupplies the deep water with oxygen. And that's a natural thing you expect because warmer water likes to stay up on the surface and it doesn't mix as well. So that, for example, might, and I say might, a lot of these things, we don't know how bad this is going to be. But these things might then increase these anoxic zones in the bottom of the ocean. Maybe, maybe not.
But it's a certainty that it's happening.
I would not say that. I would not say that. It's a certainty that anoxic zones are happening. It's an anticipated effect.
So we're not in that right now?
I would say we're not. I mean, we have these anoxic zones right now that have been caused by excess fertilizer draining off, for example, out of rivers into the ocean. But I don't know of anybody that's stuck their neck out to say that we have anoxic zones that have been caused by global warming. But that's an anticipated possibility. Yeah.
We talk about global warming and like the polar ice caps are melting, right? So would that push shorelines up because that's adding more water?
Indeed it will.
And so that would mean people that live on the shorelines, they would have to move their homes or get new homes because that end up in water?
Yeah, the question is, will melting ice raise the sea level and cause people to lose their property and homes along the sea? Yeah. Yeah, sea level is up about 8 inches already, has risen over the last 150 years or so. And it might go to several feet by the end of this century, but nobody knows for sure. It depends on how much global warming takes place between now and then. Thank you.
How much of an effect is the loss of these ice packs because of their reflective quality, where instead of reflecting, the
Yeah.
ocean becomes exposed and then the heat will sink into it?
Right, yeah, the question is really about a feedback.
Right.
Global warming melts ice, but if you melt ice, it's less, now the Earth is less reflective, so it absorbs more sunlight. Therefore, the temperature goes up even more. This is what we call feedback, and there are all kinds of feedbacks in the climate system, and this is a very good one that you've just mentioned. And it's the primary reason why polar temperatures are rising faster than global temperatures on average. Yeah, you think temperature's gone up now. Here, in the polar regions, it's twice as much. Yeah, another question.
Is the increase in atmospheric water vapor content also part of that positive feedback?
Causes of?
Is that also part of the positive feedback you were talking about?
Yes, it is. Another good example of positive feedback. If you warm the climate by any means, either by the sun getting brighter or by putting greenhouse gases, man-made greenhouse gases in the atmosphere, you raise the temperature of Earth, more water is in the atmosphere as a result of that, but water vapor is a greenhouse gas, so the temperature goes up even more. The Earth is full of feedback processes, just like the two that you two people here have just mentioned. Unfortunately, there are very few feedback processes that work the other way. Almost all of them work in the way you don't want them to, which is very disturbing, let's say.
Which ones work in the other way?
Vegetation has some. Carbon dioxide is a fertilizer. And in some parts of the world, rising temperatures will increase growth in some places, but it will decrease it somewhere else. So that would be, if you do something that increases plant growth, and plants absorb carbon dioxide. So that would be an opposing process. But there aren't many of them, unfortunately.